Hi, this is my backyard solar array. It has 15 Suniva 280 watt solar panels. Each panel has a 250 watt Enphase microinverter that reports power generation data to a central monitoring unit. In a previous video, we investigated the cause of a non-reporting microinverter in the panel and ultimately found 4 defective panels. The non-reporting panel had open circuits in 2 of its 3 photocell strings and was producing only about 10 volts instead of the normal 30 volts. That voltage was insufficient to activate the inverter, and so no power at all was produced. Further testing revealed 3 other panels with a single open photocell string, resulting in a reduction from 30 to 20 volts and a reduction in power output to 2/3 of the normal value. The system was installed 9 years ago, and in the meantime, the installer has gone out of business and Suniva went bankrupt, so basically it's my problem. In this video, we'll look at the various options for repair and upgrade, how I chose between them, and what was involved in refurbishing the system. Originally, the system had 15 times 280, or 4,200 nominal watts. Normal panel deterioration would bring that down to about 270 watts per panel, so more like 4,050 watts. But I've got 3 panels giving 2/3 power and 1 panel giving nothing, so a total of 11 times 270 plus 3 times 180, or 3,510 watts. That's a drop of 17%, of which 13% is due to defective panels. At 15 cents a kilowatt hour, I'm losing about $100 worth of power a year, so hardly a catastrophe. But it's particularly annoying to have a panel taking up space and producing 0 power. So let's look at some alternatives. I'm going to assume we can do the work ourselves, so the only cost is materials. In just the last 9 years, if you correct for inflation, the cost of panels has been cut in half. In 2016, the average was about 60 cents a watt. Now panels can easily be found for under 40 cents. In the same time, typical efficiency has increased from about 17% to as much as 23%. So in principle, I should be able to replace the whole array with, say, 5,600 watts of newer, more efficient panels in the same total panel surface area. That would give me 2,000 kilowatt hours, or about $300 worth of additional power every year, for an investment of a little over $2,000. But there's a problem, actually several problems. For one thing, modern panels are cheaper per watt, partly because they're bigger than they used to be. Typically, they're well over 400 watts, 44 inches wide and about 70 inches long, so 5 inches wider and 5 inches longer than my old panels. That's a big problem since my pole mount was custom built to accommodate 3 rows of 5 panels, 39 inches wide, stacked vertically. The vertical rails are exactly 17 feet long, and after allowing space for the clamps, that leaves just 2 inches to spare at the top. So I'd only be able to fit 4 rows of the new larger panels, leaving 20 inches of unused rail at the top or bottom. The whole array would be at least a foot wider, taking up more space in the garden. So that's one problem. Then there's the Enphase M250 inverters, which each produce a maximum 250 watts of 240 volt AC power. Enphase recommends them for use with panels up to 350 watts. But even if they worked with 400 watt panels, on really sunny days, a lot of the potential power would be wasted. I could get new microinverters with higher capacity, but they wouldn't fit my proprietary 240 volt Enphase cabling system, which even Enphase doesn't use anymore. So all of the inverters, as well as the 240 volt wiring, would have to be replaced, easily doubling the cost of the upgrade. Furthermore, even if I get new inverters, the underground power line back to the house was only designed to handle 4,200 watts, and the pole mount was only designed to support a certain weight and surface area of panels. So given those limits, I think I'll forget about a total reconfiguration of the system. Instead, let's try to find some panels that will work with the old inverters, roughly the same size as the old panels, but maybe a little more efficient. First, I looked on Craigslist. There was only one local ad for solar panels. It was for 6 Echo Solargy 235 watt panels, 10 years old but supposedly never installed, for $100 a piece. Remarkably, they're almost exactly the right size, 39 inches wide and 64.5 inches long, 1 inch shorter than the old ones. Using panels that might otherwise be discarded has a certain appeal, but on the other hand, going to all the work of disassembling the array and replacing 280 watt with 235 watt panels isn't very satisfying. So let's keep looking. Well, I've looked through several solar distributors, including A1 Solar, Signature Solar, US Solar, and Northern Arizona Sun and Wind, but I can't find anything that exactly fits the bill. Here's a 350 watt panel for just $78 each, 39.5 inches wide by 79 inches long. So they could fit vertically in a single column, but the array would have to be a foot wider than it is now. And these are 72 cell panels with a working voltage of 38 volts instead of 30 volts. So I'd have to get 5 new microinverters to accommodate the higher voltage. But here's a 60 cell panel available from US Solar, 340 watts, 68.5 by 40.5 inches for just $100 each. If they were half an inch smaller, I could just fit 2 rows of 3 new panels, but 40.5 inches is half an inch too wide. So rather than search individual sites, I searched for panels of a specific wattage. A search for 320 watt panels brought up this Renogy panel. 60 cells and almost exactly the same size as my old panels, just an 1/8 inch longer and 3/8 inch wider. At 320 watts, that's 15% more power than my old panels had when they were new, and about 20% more than they have now. The downside of these panels is that they're not cheap, over $200 a panel. With tax and shipping, it works out to 80 cents a watt, about twice as much as most of the panels I've looked at. But they're completely compatible with my old inverters, and that allow me to restore and slightly upgrade the system with minimal disruption. But how many of the old panels to replace? Despite the increased output, it really doesn't make economic sense to replace the 11 fully functional panels. So I plan to replace just the 4 defective ones. But when we went to order from the Renogy website, it turned out I could get a better deal on 6 panels, so that's what I ordered. I'll replace 6 panels and keep 2 fully functional old ones as spares in case any more panels fail. I later learned I could have bought the same panels through Lowe's, but the price with shipping would have been about the same. Anyway, now we just have to wait for the panels. Okay, it's just 4 days later and the panels are here. They were shipped UPS freight, so I was expecting them to come on a pallet, but instead they came in a regular UPS van in heavy cardboard boxes with foam padding, 2 panels in each box. And now they're unboxed in our living room. I'm pretty confident they'll work with the old inverters, but to make sure I'm going to first replace just the defective bottom center panel as a test. Okay, we're going to take off that bottom middle panel today. Okay, so it's just after sunset and I've disconnected the AC power. Now all the inverters are blinking red instead of green. So let's disconnect this AC connector from the inverter. To do that, you use this tool, these 2 big prongs, and that's supposed to release the plug. And it does, although it doesn't come easy. And now I'm going to try to release the DC side, which is these 2 connectors. And for that, this part of the tool is supposed to pinch these little tabs on the connector. Let's try this one. And these don't come easy either.
There's one. And the inverter stopped blinking. And there's two. And now we can remove either the inverter or the panel. Held down by clamps. These are metric 11 millimeter. Okay, got the old panel out. Okay, so got one panel replaced. Decided to do the bottom one. It's the easiest one to put in. And you can see the panel is about maybe 1/4 inch wider than the other ones. Length is pretty much exactly the same. And I've got it all connected. And since we're in full sun, what I did is cover the panel with cardboard and then connect the two DC lines. And of course it's turned off at the main breaker. And then I plugged in the AC feed plug and then removed the cardboard. And what happened is this indicator light showed solid green for a minute or so, and then blinking green, and then blinking red, which is typical of a DC input but no AC connection. And then finally I turned the breaker on, and after about 10 minutes started blinking green, which it still is. So let's check the current. So putting out 7.7 amps. So it does seem to be working. Let's compare that to one of the old panels. It's got a higher current, about 8.5 amps. Of course, we're in direct sun, cloudless day, and the sun is almost directly perpendicular to the panels. So it may be that the power is limited by the inverter rather than the panel. This is a 320 watt panel, 250 watt inverter. So it may be adjusting the current and voltage so that it doesn't overload the inverter. We'll have to look on the software to see how much power these are actually putting out. So just to explain here the power curves for this Renogy 320 watt panel, where this is current as a function of voltage and the green is the power as a function of voltage. And this is at standard test conditions, which is 1,000 watts per meter squared. In other words, roughly direct perpendicular sunlight, 25 degrees C, that's 77 degrees Fahrenheit. And of course, what the inverter normally does is to draw just enough current to keep the inverter at the maximum power point of the panel. And in this case, for direct sunlight,
it occurs at about 9.5 amps and about 34 volts. So that would be about 320 watts, and that is too much for the inverter. That would overload the inverter. So what the inverter does instead is draw less current to move down on this power curve to about 250 watts. And you can see that corresponds to about 7.5 amps on the current curve, which is just what we measured with the voltmeter. On the other hand, with the old panel, which had a 280 watt maximum, would be much closer to the maximum power point. And in fact, you remember we measured about 8.5 amps. That corresponds very closely to the specified amperage at the maximum power point, which is about 8.8 amps. Okay, so the old panel was producing about 8.5 amps, probably at about 31 volts, whereas the new panel was producing about 7.7 amps, probably at about 37 volts, in each case producing just a little bit over 250 watts. Now you might ask, why bother with a 320 watt panel when your power is limited to 250 watts by the inverter? Well, that's only the case when you're in this area of the curve that is very close to full perpendicular sun. About 90% of the time you're going to be in this area of the curve, either because of clouds or partial shading of the panel, or the sun's coming in at an angle. And in this area, you're always going to get more power from a 320 watt panel than from a 280 watt panel, actually about 15% more power. And in fact, if we look at the data from the first day here, we see that we are getting substantially more power from that new panel than we're getting from the surrounding panels. And again, it's about 15% more power. And if we compare that to the old defective panel, it's almost twice as much power as the old panel. So that looks pretty good, and I think we'll go ahead and replace 6 panels here, including, of course, the 4 defective panels.
Now 3 of the defective panels are in the second row from the top, so obviously we're going to have to remove the whole top 2 rows of panels. So how to get up there? Well, it turns out this whole array is mounted on a gimbal, so that if we crank this up and down, we've got a crank down here, we can adjust the angle of the array. And of course that's to maximize solar exposure with the changes of season. But if we crank this all the way down, that still leaves the top row of panels about 7 feet off the ground. So I think what we're going to have to do is detach the crank completely, and then we can pull this bar further down, tilt the array all the way backwards, and maybe that'll bring those panels down maybe about shoulder high or chest high, and then we can fairly easily remove and replace them. Okay, so you can see that's exactly what we've done here. We've detached the crank completely and tilted the array all the way backwards, and then chained down the bar to the pole to keep it in place. And that made the panels quite easy to remove. They were about chest high, so easy to work on. We did use a step ladder, but only when we needed to reach over one of the panels to tighten the clamps between the panels. Otherwise, everything went pretty smoothly. Well, now that we got all the panels out, I think I've identified the problem here, and it's probably basically moisture penetrations. So this is the panel that has two broken strings, one on each end, and then the middle string is still functional. And you can see that these two connections have some discoloration, and I think they've basically come apart. And when I look at these panels, the strings always have some voltage, but then when you try to draw current, the voltage drops way down. So I think there is still a slight connection here, but not enough to support significant power from the panel. Here's maybe a better view on the close-up. I think you can see the discoloration on this terminal as opposed to these nice shiny silver terminals. Although I'd have to say it's much more obvious to the naked eye than it is on the camera. Okay, got all the panels installed. We decided to move the new one from the bottom and put all 6 new ones on the top. Because it'd be easier to replace the ones on the bottom if another one goes bad. Everything's already connected and they're all blinking green. So I guess they're all working. So I just have to release the chain here and reconnect the crank. Okay, camera's rolling.
Oh no. I'm afraid. Ready to go up?
Yep.
No, go up. Am I supposed to help you?
No, I just don't want to do that.
Keep going, keep going. Chain will keep it from going too far. Got another 4 inches. Another 3 inches.
I'm at the height of my height here.
Well, you grab it
Down here.
down there. Keep going. Another 2. Keep going. Keep going. Another inch. Getting there. Going.
Gotta get heavy.
I know. You're almost there. Another 1/4. And you there. You ain't doing nothing.
Okay, so we're back in operation. Pretty sunny day. Let's go check the software, see what's going on.
So here are data from the first day of operation. And you can see, first of all, that all the inverters and all the panels are working just fine. From the 6 new panels, we're getting around 1.4 kilowatt hours each. And from the old panels, anywhere between 1.1 and 1.2 kilowatt hours. So there's nothing wrong with any of the inverters. All the problems were due to defective panels. And if we take the ratio of the new panels to the old panels, we see that on average we're getting 24% more power from the new panels than from the old panels, which is actually a little bit better than I expected. Now here's a really sunny day. It was sunny almost all day long. And here we're getting about 1.81 kilowatt hours in the new panels versus about 1.55 kilowatt hours in the old panels. And that's only an increase of about 17%. So as you expect, when you get a very sunny day, you're going to get more time when the power is limited by the microinverter and not the panels. So it's a slightly smaller difference. On the other hand, if we look at a very overcast day, so here we're only getting about 1/3 as much power as we got on the sunny day. And in that case, in the new panels, we're getting an average of about 565 watts in the new panels versus about 456 watt hours in the old panels. And again, we're back to an increase of about 24%. So again, when we have relatively weak sunlight from the overcast skies, we're going to be limited by the panels. So expect a larger difference in the new panels. And finally, here are data from July 8th when it was sunny all day, but also very hot. I think the high was 96 degrees. And of course, these panels have a negative temperature coefficient. In other words, the hotter they get, the less power they produce. So here we're getting slightly less power than we got on a sunny but cool day, but we're back to the new panels yielding 25% more power because the panels have again become the limiting factor. So overall, I think on average we're going to get almost 24% more power from the new panels because it's only on rare occasions, on cool sunny days in the middle of the day, that the inverters will be limiting the power. Okay, so it's working fine, but was it worth the cost? Well, let's estimate how much power we're getting from it. As we calculated earlier, with the 4 defective panels, we had a nominal 3,510 watts of solar capacity. That was based on an estimated 270 watts for each of the old panels. I'm confident we're getting at least 20% more power from each of the 6 new panels. So the new total nominal capacity would be 9 times 270 plus 6 times 1.2 times 270. That's 4,374 watts. That's an increase of 864 watts. It seems like I get just about 1 kilowatt hour a year for each watt of nominal capacity. And we're paying about 15 cents a kilowatt hour for grid power. So savings per year should be 864 times 15 cents, or $130. We spent about $1,600 on the panels, so the cost should be recovered in about 12 years, assuming electricity rates stay the same. Of course, with AI data centers going up everywhere, it's highly likely power is getting more expensive over the next few years, so that would shorten the payback period. Anyway, I'm pleasantly surprised that I could get that much of a boost in power by replacing 280 watt panels with 320 watt panels, and that the microinverters will automatically adjust to prevent overload of the system. Thanks for watching.